This is the third video lecture for Chapter 15, Acids and Bases. So we spent a lot of time discussing acids in the previous video lecture. Now I'd like to focus on strong bases. So here we're showing the sodium hydroxide, which is a strong base, and it completely dissociates in water to form sodium plus and hydroxide ions. And the nice thing is that once we start talking about bases, you can think about them as the converse to acids, so there's a lot of relationships between acids and bases you'll see when we start to study them. Now the stronger the base, the more willing it is to accept protons, and we're using water as the standard acid. For strong bases, practically all molecules are dissociated into hydroxide ions, or they all accept protons. And there's strong electrolytes and multi-hydroxide strong bases completely dissociated. And the hydroxide concentration is going to be equal to the strong base concentration times the number of hydroxide ions. So this means you have to take into account the number of hydroxide ions in the balanced chemical equation. So the strong base concentration will be equal to the hydroxide concentration in that example. But if we're talking about calcium hydroxide, so remember, calcium hydroxide has a formula of CaOH, and there's two OHs. So when that dissociates, it forms calcium 2 plus OH minus, but to balance it, you have to have a 2 in front here. So if the concentration of the calcium hydroxide is 0.2 molar, then because it's a 1 to 2 mole ratio, the hydroxide concentration will be 0.4 molar when it dissolves. So let's look at a practice problem. They want us to calculate the pH of a 0.001 molar barium hydroxide solution and determine if it's acidic, basic, or neutral. So we first have to write the balanced chemical equation, and notice that this is a one-way reaction, so they've only have the one direction arrow because this is a strong base. There is no equilibrium set up with the barium hydroxide dissolving. So the hydroxide concentration is going to be twice that of the OH, the barium hydroxide concentration. So the OH concentration is 2.0 times 10 to the minus third, because if we were to set up an ice table, all of that dissociates. So it'll make 0.001 barium hydroxide, but it'll make 0.002 molar hydroxide. So now that we have the hydroxide concentration, we can calculate the pOH, which is the negative log of the hydroxide concentration. There we get a pOH of 2.7. And we know that if the pOH is less than 7, it's a basic solution. Now, I typically have trouble going back and forth between pH and pOH. It's too easy for me to get it confused. So what I'd like to do is take that pOH value and convert it into pH. So the pH equals 14 minus the pOH, because remember, the pH plus the pOH equals the pKw, which is 14. So pH equals 14 minus the pOH, so we get a pH of 11.3, and that's higher than 7, so that pH of greater than 7 is basic. So that way I don't have to keep it straight which one is which. I can kind of think of most things in the pH scale. Now weak bases, remember, weak bases are weak electrolytes, and they only partially dissociate. So in a weak base, only a small fraction of the molecules accept the protons because they're weak electrolytes. And most of the weak base molecules do not take protons from the water because they are weak, and this is much less than 1% ionization in water. So for example here, where we have the ammonia dissolving in water, most of that are dissolved ammonia molecules, and you have a few ammoniums where it's actually been protonated by the water to form the ammonium. So remember that NH3 has a lone pair that can accept the proton from the water. And remember, for weak bases, the hydroxide concentration is much less than the weak base concentration because it only partially dissociates. The equilibrium lies mostly towards the left. Now finding the pH of a weak base solution is very similar to finding the pH of a weak acid. And just like there are Kas already known for the weak acids, there are Kbs known and published for many of the weak bases. So remember, the Kb is the equilibrium constant for the ionization of that base. Now I just want to talk about some structures of our amines. So amines, those blue spheres represent nitrogen molecules, and ammonia, remember we said, has a lone pair. So anytime you see a nitrogen with a lone pair in a molecule, you should think of that substance as being basic, so a place where it can be protonated by an acid. Methylamine is another type of base. So you've got a methyl group here, so this represents a CH3 part of the molecule, and this is another NH group, so you got hydrogen, that's a hydrogen, and that's a hydrogen, and that's a nitrogen. And this is a pyridine, so this is a ring of carbon, so each of those black spheres represents a carbon. And you have a nitrogen here with a lone pair, so that's a place that can be protonated. And anytime you have a nitrogen with a lone pair, it can be protonated, so this is why we think of these amines as bases, because they can accept protons. So one of our practice problems is finding the pH of a 0.0015 molar morphine solution. So this is the structure of morphine, and even though this Lewis dot structure doesn't show it, there's actually a lone pair on that nitrogen. So this morphine is a weak base. And the Kb, if we were to look that up in a table, we'd find that the Kb is equal to 1.6 times 10 to the minus 6. Rather than writing out the entire formula for morphine, since it is so long, I'm just going to say B, which represents the base. I'm just going to put some lone pairs on it just so you can easily see that it has a nitrogen with a lone pair to accept the protons. And that base will take a proton from the water, and the base becomes protonated, forming the BH+, and that's how you get the hydroxide ions in solution. So we set up our ice table. Initially we have 0.0015 molar of the base, and we have none of the protonated form of the base, and we have none of the hydroxide, or we have a negligible amount. Because remember, there is hydroxide in there due from the autoionization of water, but we're not going to worry about it since it's so small. Now, if we start off with no products and some reactants, that means the equilibrium, the reaction is going to have to proceed to the right to go to equilibrium because the Q value is less than the K value. So our change is minus X, and we'll be increasing the product side. So we plug that in to find the equilibrium concentrations into our ice table. Now that we've got our ice table set up, we can set up our mass action equation. So our products over our reactants, so the BH plus times the hydroxide concentration over our initial B concentration. And we can plug those values in from the ice table. And again, we're going to assume that X is so small in comparison to the 1.5 times 10 to the minus third. We're going to use that approximation. So if I plug in my Kb values and I plug in my concentration for our B minus, and we square the X values, multiply both sides by 1.5 times 10 to the minus 1, and then take the square root, I should get an X value in my calculator of 4.9 times 10 to the minus fifth. That tells us our hydroxide concentration. Now I'm just going to double check, since I did do an approximation, to see if that's okay. My X value over my initial concentration times 100 is 3.3%, which is less than 5, so I'm good to go. My approximation is valid. Since I've determined my hydroxide ion concentration is X, and we said that's 4.9 times 10 to the minus fifth, I'm going to find the POH. And the POH is just the negative log of the hydroxide concentration, and I get a POH value of 4.31. And I'm not quite done yet because they wanted the pH. Well, since the pH plus the POH equals 14, I can use that relationship to find my pH. So pH equals 14 minus the 4.31, and I get a pH value of 9.69. So let's talk about some acid-base properties of salts. Remember, salts are ionic substances and they're water-soluble ionic compounds. Salts that contain the cation of a strong base and an anion, that is the conjugate base of a weak acid, are basic. For example, sodium bicarbonate solutions are basic. And the reason why the solution of the salt of sodium bicarbonate is basic is that the sodium ion, the sodium plus, is the cation of a strong base. So that's sodium hydroxide. Remember, strong bases make weak conjugate acids. Well, if it's so strong that we can classify it as a strong base, the conjugate acid we will consider to be neutral. So the sodium plus is a cation from the strong base. So we consider that to be neutral. But the bicarbonate ion is the conjugate base of the weak acid, the H2CO3. So the conjugate base of the weak acid is a base. So the HCO3 minus is a base. Therefore, the sodium bicarbonate solution as a whole is basic due to the contributions of the bicarbonate ion, which is basic. Now, salts that contain cations that are the conjugate acid of a weak base and the anion of a strong acid are acidic. So what does that mean? Ammonium chloride solutions, if I were to make a solution of that and measure the pH, I'd find that it was acidic. This is because the NH4 plus is the conjugate acid of the weak base NH3. So if you've got the weak base in there, it will form the NH4 plus, which is an acid. But the chloride is the anion from a strong acid, so like HCl. So we consider that to be a neutral anion in acid-base terms. So since the Cl minus is neutral and the NH4 plus is acidic, the overall solution is acidic. Every anion can be thought of as the conjugate base of an acid. Therefore, every anion can potentially be a base. For example, A minus plus water are going to make the HA, the acid form of the A minus. The stronger the acid is, the weaker the conjugate base is. An anion that is the conjugate base of a strong acid is pH neutral. So the chloride anion, when you add it to water, if you think about it making HCl, HCl is a strong acid. It's going to completely dissociate. So we see it going back in the reverse direction. So that's where we have, that's why we say the chloride is neutral. So since HCl is a strong acid, this equilibrium lies practically completely to the left. It's a one-way reaction, so the chloride is, we consider it to be neutral. An anion that is a conjugate base of a weak acid is basic. So for example, F minus, when combined with water, will make HF. HF is a weak acid, and that has an equilibrium established with it. Notice we have the double-ended arrows to represent the equilibrium. So since HF is a weak acid, the position of this equilibrium favors the right. So we're going to look at some ions and determine if the given anion is basic or neutral. HSO4 minus, this is the conjugate base of a strong acid. So the sulfuric acid is where this came from, so the H2SO4. So since this came from the strong acid, we consider the HSO4 minus to be neutral. What about SO4 2 minus? SO4 2 minus is the conjugate base of a weak acid. Therefore, we consider it to be basic. So here's where we find the SO4 2 minus. So whereas the HSO4 up here comes from the strong sulfuric acid, the HSO4 minus is neutral. Here, the SO4 2 minus comes from the weak acid HSO4 minus. So we consider this to be a weak base. So the HSO4 minus is a weak acid. It forms its conjugate base, the SO4 2 minus, and this is a weak base. So the SO4 2 minus is a basic anion. Now let's look at the relationship between Ka of an acid and Kb of its conjugate base. Many reference books only give the Ka values in tables. This is because the Kb values can be directly calculated from the Kas. So notice if we've got the reaction HA, some generic equation HA forming A minus and H3. Here we have the mass action equation for the A is products over reactants, the A minus times the H plus over the HA. Now if we write that equation in reverse, because A minus is the conjugate base of the HA, so this is the basic form of this reaction. This is, and the top one was the acidic form. So the A minus base reacts with the water and it becomes protonated to form its conjugate acid, the HA plus the OH minus. So the Kb for this reaction is products over reactants. So this is the HA times the H plus concentration over the A minus. And remember, when you add equations, you multiply the K's. So we learned that in our previous chapter. So I'm going to add these two equations together. And notice that the HA's on both sides cancel out and the A minuses cancel out. What I'm left with is two waters, and those two waters can then ionize to form H3O plus, the hydronium ion, and the hydroxide ion. So this should look familiar to you from the auto-ionization of water. And we know that the K for that expression is the Kw, which is the products over reactants. And notice we have no mixtures on the reactant side, so the water is pure, so it doesn't show up in our mass action equation. So the Kw equals the H plus concentration times the OH concentration. So the Ka times the Kb equals the Kw. So this is why tables in books typically only list the Ka, because if you know the Ka and the Kw, you can calculate the Kb. So let's find the pH of a 0.1 molar sodium formate solution. Well, sodium formate is a salt, and it's going to dissolve in water to make sodium and the formate ion. So this is a one-way reaction. But the formate ion will then react with the water to make formic acid and the hydroxide ions. And if we look up in tables, we can find that the Ka for the formic reaction is 1.8 times 10 to the minus fifth. Now we said that the formate is a basic ion, so it makes a base in solution. So we see we have the generation of the hydroxide ions when dissolved in water. So this is a base. But they only gave us the Ka, so we're going to have to find the Kb to solve this problem. So using Ka times Kb equals Kw, Kb equals the Kw times the Ka, so that 10 to the minus 14th divided by the Ka equals 5.6 times 10 to the minus 10th. So now we now have our Kb value for the formate ion. Now let's set up our ice table. Initially we have 0.1 molar of the formate ion. And we're going to do our change. We're going to lose some amount of formate ion as we make the formic acid and the hydroxide ion. And we get our equilibrium concentrations. Now we can substitute these values into our mass action equation. And I'm going to assume that the change in our concentration of the formate ion is very small, so I'm going to use my approximation. And I'm going to plug my Kb value in, and I'm going to plug in my initial concentration. Remember I made my approximation, and then we've got our x squareds here because we're multiplying these two. So I multiply both sides by 1 times 10 to the minus 1 and take the square root, and I get an x value of 7.45 times 10 to the minus 6th. Okay, so what did I just find? So I found my hydroxide concentration. But they want to know the pH. Well, if I've got the hydroxide concentration, I can calculate the pOH, and then from the pOH I can calculate the pH. Now I'm just going to double check to make sure that my approximation is valid. So I plug in my x value over my initial, multiply it by 100, and it's definitely much less than 5, so I'm good to go. Now I'm Going back to the problem, since I'm okay doing the approximation, I'm taking the negative log of my hydroxide concentration to find my pOH, which is 5.13. Not quite done yet because they want the pH. So I take 14 minus the pOH, and I get a pH value of 8.87. Let's talk about polyatomic cations as weak acids. Some cations can be thought of as the conjugate acid of a base. Others are the counterions of a strong base. Therefore, some cations can potentially be an acid. MOH2 plus, and when it reacts with water, forms the MOH and the hydronium ion. So the stronger the base is, the weaker the conjugate acid is. A cation, that is the counterion of a strong base, is pH neutral. A cation, that is the conjugate acid of a weak base, is acidic. So for example, ammonium, so NH4 plus, when you put it in water, it will give up its proton to form ammonia, so that's the conjugate base of the acid. So, and remember, NH3 is a base. So since NH3 is a weak base, the position of this equilibrium favors the right. Also, metal cations can be weak acids. Cations of small, highly charged metals are weakly acidic, but alkali metal cations and alkaline earth metal cations are pH neutral. Now these cations are hydrated. For example, we've got an aluminum 3 plus with 6 water molecules around it. So this is what we're showing here in this picture. So we have an aluminum, it's got a 3 plus charge, and you've got 6 water molecules coordinated to it. If another water molecule comes near, it will pick up one of the protons. And actually it's showing it's losing this proton over here in the picture, but it doesn't make here nor there. But the water will pick up a proton to make the hydronium ion, so this is the H3O plus, and leave behind an OH group. So this is that OH group on the aluminum. This is because the aluminum, think about this aluminum as being very highly charged. So it's got a very positive charge. So it's going to be pulling electron density into it. And as it pulls electron density into it, that means that there's less available for the proton on the water here. So that proton says, fine, you're not going to share any electron density with me. I'm going to go somewhere else and get my own electron density. So it dissociates and it protonates the water here to make the H3O plus. So when you have a small, highly charged metal ion, it pulls electron density in so much that the water molecules around it that coordinate, one of those can actually lose one of its protons, and that's how it makes an acidic solution. We've got some examples here, and they want us to determine if the given cation is acidic or neutral. So this is a pyridinium. So this is a pyridine molecule where the nitrogen is protonated. So hopefully you should see that this is the conjugate acid of a weak base. So if it's the conjugate acid of a weak base, so the conjugate acid of this weak base is the acidic conjugate acid. This is the conjugate acid of the weak base, so therefore it's acidic. Calcium 2 plus. This is a counterion of a strong base. So if it came from a strong base such as calcium hydroxide, we consider this to be neutral. Whereas with chromium 3 plus, this is a highly charged metal ion, and we can consider this to be acidic, because remember, like the previous example of the aluminum with 6 water molecules around it, same thing going on with this chromium. But remember also too, we said that the alkali metals don't do this and they're neutral, so that's why the calcium 2 plus we said was neutral. So in the first case, in part A, we have the protonated nitrogen, so that makes it an acidic. In B, we have the alkali or alkaline earth metal, and those are, we said, were neutral. And then highly charged metal ions, we said, would produce an acidic solution when they associate with waters. So let's talk more about classifying salt solutions as acidic, basic, or neutral. And I know this can be a bit confusing, especially when this is new to you. So if the salt cation is the counterion of a strong base and the anion is the conjugate base of a strong acid, it will form a neutral solution. So if the ions, the cation and the anion both came from strong acids and strong bases, it's neutral. Now if the salt cation is the counterion of a strong base, that produces a neutral cation. But if the anion is from the conjugate base of a weak acid, that anion is basic. So if the anion is the conjugate base of a weak acid, it's going to be basic. So if you've got a neutral thing and a basic thing, it's going to mean that the overall thing is basic. So for example, NaF-, the sodium came from, it's an alkali metal, we say those are neutral. The F-, you can think of it coming from HF, which is a weak acid. So the F- is a conjugate base. So the NaF sodium fluoride is actually a basic when dissolved in solution. It'll make a basic solution when the sodium fluoride is dissolved in water. If the salt cation is a conjugate acid of a weak base and the anion is the conjugate base of a strong acid, it will form an acidic solution. So notice if you've got something from a weak base in there, the conjugate acid is going to make this solution acidic, but the conjugate base of the strong acid we consider to be neutral. So the NH4, for our example, the ammonium chloride, the NH4 plus came from ammonia, so ammonia is a weak base, so the ammonium is a weak acid. And then the chloride came from a strong acid, think of hydrochloric acid. So if that came from a strong acid, it makes a neutral ion. So ammonium chloride is overall acidic. Now if the salt cation is a highly charged metal ion and the anion is the conjugate base of a strong acid, it will form an acidic solution. So remember, the nitrate came from nitric acid, and nitric acid is a strong acid, so the nitrate anion is neutral. But the aluminum is highly charged metal ion, it makes an acidic solution. So overall the aluminum nitrate solution is acidic. If the salt cation is the conjugate acid of a weak base and the anion is the conjugate base of a weak acid, the pH of the solution depends on the relative strengths of the acids and bases. So remember, if you had two strong things, strong acid and strong base that form the cations, it produces the neutral salt. But if you have both the weak acid and the weak base, you've got to figure out which one's stronger. So let's look at ammonium fluoride as an example. So ammonium we consider is the conjugate acid of ammonia, which is a base, weak base, and the F- is the conjugate base of the weak acid HF. So since HF is a stronger acid than ammonium, the Ka of ammonium is larger than the Kb of the F-, therefore the solution will be acidic. Okay, so let's do some examples to see how well you understand that. So strontium chloride. Is it acidic, basic, or neutral? So the strontium 2 plus is the counterion of a strong base. So the pH is neutral. The chloride is the conjugate base of a strong acid. So think about hydrochloric acid. So the pH is neutral. Thus the solution will be overall neutral. You can think of strontium, remember that's one of your alkaline earth metals, so that's going to be neutral. Aluminum bromide, hopefully you said that the solution would be acidic. The aluminum 3 plus is a small, highly charged metal ion, so that forms a weak acid. The bromide is the conjugate base of a strong acid because HBr, think of HBr, that's a strong acid. So the pH of that Br- is neutral. So the overall is acidic due to the aluminum 3 plus. In this last example here, the CH3NH3 plus is the conjugate acid of a weak base. You have the protonated amine. And the NO3 minus is acidic. It's the conjugate base of the strong acid. So with the methylamine, This is actually the protonated form of the methylamine. This is a conjugate acid of a weak base, so this component is acidic. Now the nitrate, the NO3-, that's the conjugate base of a strong acid. Thus its pH is neutral. So if one part is acidic, the other part is neutral, the whole thing has to be acidic. What about sodium formate? Sodium is a counterion of a strong base. That's an alkali metal, so that's pH neutral. The formate is the conjugate base of the weak acid, formic acid. So that's going to be basic. So if you've got a neutral and a basic, the whole thing has to be basic. In our last example, the ammonium fluoride, there's a bit of a tricky one because you've got ammonium and the fluoride. Both of those come from weak acids and weak bases. So the ammonium is the conjugate acid of a weak base. It's acidic. The fluoride is the conjugate base of the weak acid HF, and that's F- is going to be basic. So we have to compare the relative strengths of the weak acid and the weak base. So the Ka of ammonium is larger than the Kb of the F-. So since the Ka is larger, the solution will be acidic.